Geometric probabilities, let's compare these to binomial. Both have to categorize into success and failure. Both have to have the trials independent of each other, which makes sure that the probability of the success will not change. Now with binomial, the number of trials is fixed. You're going to have 8 people selected, what's probably get 5 successes. But with geometric, this is the big difference, that you just keep selecting until you get your first success, and then you're done. So what's probably you get your first success on the 3rd trial, you'd have to have a failure, and then a failure, and a success, and you would be done. So you don't know how many trials you're going to look at with geometric. With binomial, it's fixed. Well, if we look at this, with binomial, you can signify, you could say, hey look, x is distributed binomially with n trials and a success rate of p, and x, the random variable x in binomial, is number of successes in n trials. And so over here we'd have x would be anywhere from like 0 through 5 successes if there's 5 trials. And what tends to happen, if the probability of success is somewhere in here like about 0.4 or something, then the binomial distributions would tend to be more bell-shaped. But with geometric, the only parameter is p, the success rate, because the random variable is going to be the trial in which we get our first success. And so unlike binomial, where you can have 0, because you can have 0 successes out of n trials, with geometric, you can't have your first success until the first trial. So the smallest value for x could be 1. It's kind of like a lawyer. You can't get a success unless you have a trial, unless you settle on a court or something like that. And it'd be interesting if you were an attorney suing the NBA, and then what would it mean to settle on a court? I don't know, but anyway, so we got this right here. Do you agree that the distribution then for geometric is always skewed right? Your greatest trial in which you'd get a success would be the first trial. It all goes down from there. So you'll understand that more as you look at a few more geometric probabilities, but the greatest success, or the value for x that has the greatest probability associated with it, is that you're going to get your success on the first trial, because it keeps depleting after that. And then again, binomial tends to be more bell-shaped. So let's look at a problem. Suppose that 12% of Americans state that basketball is their favorite spectator sport. If we randomly select Americans, find the probability that our first person who would consider basketball as their favorite spectator sport was the 3rd person chosen. You don't really need much of a formula for this. You just have to think it through logically. In order to get your first success on the 3rd trial, you must have started off with 2 failures, 2 people that didn't consider basketball to be their favorite spectator sport, followed by the success, the first and only success on the 3rd trial, and we are done. So with geometric, it's when will you get your first success? We're just considering the probability we got our first success on the 3rd trial. So in this case, we had 3 things that were being selected, so it was a failure and a success. So we would say that this probability is 0.88. Probably the first person was a failure, times 0.88, and then times the 0.12. Multiply those together, and you've got your answer. So I would argue that with geometric, it's pretty straightforward. You don't even really need a formula. Just think it through. 2 failures, first success was on the 3rd trial. Problems get a little trickier if we say something like this. Again, same scenario, success rate, failure rate. You recognize that from proportions, success rate, failure rate. Randomly select Americans until we find, or I'm sorry, if we randomly select Americans, what's the probability we find the first success somewhere among the first 3 people chosen? Well, you want to reason through what that would mean. You can have your first success somewhere among the first 3 people chosen, but once you get your first success, you're done. So here's the scenarios. You could get your first success on the first person chosen. In that case, you'd be done. Or you could get your first success on the 2nd trial, which would mean you had a failure followed by a success. Or you can end up with 2 failures followed by a success. Either one of these 3 scenarios would cause you to get your first success somewhere among the first 3 chosen. Then we go back to that basic probability thing where we said that or means add, and means multiplied, provided that you're selecting two or more things. So all we do is say, oh, the probability we get our first success on the first trial is 0.12, or plus, probability we get our first success on the second trial is 0.88 times 0.12, or that we get the first success on the third trial is 0.88 times 0.88 times, I suppose I should use the color coordinator, okay, right there. So if you add those three up, you've got your probability. You get your first success somewhere among the first three trials. And then this is what I was saying a moment ago about the fact that the greatest probability in a geometric is always associated with the first trial. Because this is 12%, the probability of getting your first success in the second trial is 88% of 12%. So the probability goes down. The probability of getting your first success in the third trial is 88% of the previous result. And that's where we get the term geometric. It's actually a geometric series, if you remember from Algebra 2, where the starting value, the first term is 0.12, and then the multiplier, the common ratio, is 0.8. You keep multiplying by 0.8. So it gets its term, geometric probability, from the fact that this is a geometric series. We're adding up these probabilities, or a geometric sequence if you just want to look at them separately. And then, again, going back to the success rate and the failure rate, this is about the trickiest one we'll see. What's the probability we get our first success occurring on at least the fifth person chosen? So we just want to think that through, and there's a couple ways that we could do that. We see at least 5, so if we want to find the probability that it took more than the fourth person chosen, it was at least the fifth one before we got our first success, we could do it this way. We could do 1 minus what you get when you add up all the probabilities leading to you getting your first success somewhere among the first 4 trials. So if you take this probability that you get your first success among the first 4 trials, and you do 1 minus that, then that would be equivalent to this probability that it took until at least the fifth person chosen to get your first success. Now I'd rather push you a little bit. I'd rather you did something that's a little quicker and more beautiful, more elegant in a mathematical approach, and that would be this. What guarantees that it would take until at least the fifth trial until you get your first success is starting out with 4 failures. If you start out automatically with 4 failures, then you're guaranteeing that you have yet to see your first success. So this is actually equivalent to the probability of it taking until at least your 5th trial to get your first success. That's the quickest thing by far. This is faster than doing that. So it's 0.88 to the 4th power, and you are done. If you do 0.88 to the 4th power, that's the probability that you started out with 4 failures. That guarantees that your 5th success isn't occurring until at least your 5th trial. So just a little bit of fun with geometric. Good luck with those.